this meeting as well. At the first, I'm so grateful from FGCP and IPM Math groups for organizing this number theory seminars, and I'm also so grateful for IPM Math group, especially Dr. Hedayatzadeh and Dr. Ahmadi for permitting me to have a talk in this seminar. And from IPM Math group, let me to say a warm hello and welcome to all. And now I will share my screen and will start my talk. Simi, can you see my screen now?
Yes.
Yes. Oh, okay. I will start. So the title of my talk, as you see, is Polio and pre-Pólya groups in dihedral number fields. And the outline of my presentation is organized as follows. At the first, and as usual, we will give a brief historical background, and we'll introduce some basic notations in this area, such as integer valued polynomials, Polio fields, and Polio groups as well. And then using some results, I will talk about Polio groups in odd prime degree dihedral fields. By an odd prime degree dihedral fields, I mean a number field K with extension degree L for L and odd prime, such that the Galois closure of K over Q has the Galois group isomorphic to D index L, the dihedral group of order 2L. And three main results in this section would be an exact sequence of Polio groups, which relates the Polio group of an odd prime degree extension of Q and Polio groups of its subfields. Then I would talk about maximum ramification, and will give an upper bound on the number of ramified primes in Polio odd prime degree number fields. And finally, I would talk about a result which is an improvement of Ishida results about divisibility of class number in this type of number fields. In the section 3, I will define the notion of relative Polio group, which is a generalization of Polio group, and in particular, I will talk about a generalization of Xanthoma exact sequence, where the Xanthoma exact sequence is a main tool for studying the Polio group and Polio fields. And finally, I will consider the more difficult case, namely non-Galois extensions, and after introducing the notion of pre-Polio group due to Chabert, I will talk about some results about pre-Polio group of even dihedral extension. And finally, I will give an upper bound on the number of ramified prime in Polio D4 fields. It should be mentioned that the results in section 2 and section 3 are a part of our results in a joint work with my PhD advisor, Dr. Ali Rajai, whereas section 3 is about my recent work, my research works in IPM. So let me start with these classical but interesting results due to George Polio in 1919, where he has proved for a polynomial f(x) with rational coefficients f maps z to z, if and only if it can be written as a z-linear combination of these polynomials, namely polynomials choosing n of x. And please note that in the denominator of these polynomials, factorial exists, and we will say soon there are a generalized notion to factorial due to Manjul-Bhargava, which is related to studying the Polio fields and Polio groups as well. More generally, let K be a number field with a ring of integers OK, and define the ring of integer valued polynomials over OK to be a set consisting of all polynomial f with k rational coefficients, such that f maps OK to OK. And Polio was interested in determine for those number field k rather than q, we could find a result similar to this formulation. So let j index n of k for each non-negative integer n is defined to be a set consisting of all leading coefficients of degree n integer valued polynomial of x along with 0, and one can show that this isomorphism holds. We will not prove here, but by this proposition, one can show that such a big projective OK module is free, and now we have int of OK is a free OK module for every number field k. But finding an OK basis for int of OK such that it has exactly one member from each degree may be difficult to describe. And int of OK, and we call int of OK has a regular basis if int of OK has such basis. For the first example, as we saw, by Polio result, the set of all choosing n of x polynomials form a regular basis for int of z. And as I said, Polio was interested for finding for those number field k, int of OK has a regular basis, and he has proved that int of OK has a regular basis if and only if the all ideals j index n of k are principal. We refer to j index n of k as the characteristic ideal of k. And in a modern version, one can show that the characteristic ideals are inverse of the generalized factorial ideals of Bhargava. Indeed, Manjul Bhargava using an interesting notion, namely p-ordering, define the notion of generalized factorial ideals, and so we find an equivalent criterion for int of OK has a regular basis that is equivalent to all generalized factorial ideals of K are principal. However, we will not use here this, and instead of these two criterions, I will use a criterion, an equivalent criterion due to Ostarovsky. Indeed, in the same year after immediately after Polya's paper, and in the same journal with the same title, Ostarovsky has proved that int of OK for a number field OK with ring of integers OK, int of OK has a regular basis if and only if all the ideals p index q of k are principal. We refer to p index q of k as Ostarovsky ideals, and they are defined to be product of the all maximal ideals of k with the same norm q. Note that if there are no maximal ideal of OK with ideal norm q, by the convention we take pi index q to be the whole ring of integers OK. Summing up these arguments, in 1982, Hans Zantema introduced the notion of Polya field. That says a number field K is called a Polya field if the following equivalent conditions hold. And as I said before, I will use the third criterion, namely principality of the all Ostarovsky ideals for studying the Polya group and Polya fields as well. It should be mentioned Zantema's paper is great contribution for the studying Polya fields, and there is many there are many interesting results which we used throughout this presentation. To be make more clear the notion of polio fields, it will be good if we have some examples, and the first example is an obvious example. As you know, every class number 1 number field should be polio, but not conversely, as we will see in the next slides by Hilbert's theorem. There are infinitely, for instance, many polio quadratic fields with no class number 1. And as another examples, we can refer to cyclotomic fields or abelian number fields with only one ramified primes due to, again, Zantemann. And by more new results, for instance, some results due to Lerish or Lekish in French. I'm sorry, I cannot speak French. For a number field K, its Hilbert class field, namely maximal abelian unramified extension of K, always is polio, and in a special case, genus field of an abelian number field is always polio. 15 years later of Zantemann paper, Cohen and Chabert, as a measure of the abstraction for K to be polio, introduced the notion of polio group, which we denote by POK, and is defined to be the subgroup of the ideal class group of K, generated by the classes of all Ostrovsky ideals. And here is a simple but an important remark due to Ostrovsky that says whenever K over Q is Galois, then the polio group of K would be generated by the classes of Ostrovsky ideals for corresponding ramified primes. And this is important because this makes more easier investigating Polianus and polio group in the Galois extension rather than non-Galois one. Because as you know, whenever K over Q is Galois, the all prime ideals of K above a prime P have the same class residual degrees, and this implies that for a non-ramified prime P in K, the corresponding Ostrovsky ideals of P would be automatically principal. We will back to this slide at section 4 for talking about a non-Galois extension. So now let's K over Q be a Galois extension, and using some cohomological tools due to Böhmer-Rosen in 1963, the polio group of K would be equal to the subgroup of a strongly ambiguous ideal class of K. And this is an interesting result because we can refer to Hilbert's results as the first and first important results about the structure of the polio group and polio fields by now. Indeed, studying the ambiguous ideals in quadratic fields, which is introduced by a genus theory due to Gauss, Hilbert proved that the order of the subgroup of a strongly ambiguous ideal class in a quadratic number field K is given by this formula, and we know that the Hilbert result is the same as the order of the polio group for quadratic number field. Please note that a polio quadratic field can have at most 2 ramified primes, and in a more general case, namely whenever K over Q is a Galois extension with Galois group G, then Zantemann found an interesting exact sequence which relates the polio group of K with ramification and the first cohomology group. And this is, as I said, is an important and powerful tool for studying polio group. And as a corollary, as you see, we see that if the class number of K and the extension degree of K over Q are co-prime, then K is a Polio field, but not conversely. And I just again refer to Hilbert's results for finding infinitely many Polio quadratic fields with even a number fields. And okay, so Semi, sorry, I don't know the screen. Is there any comments or questions?
No.
Or should I continue?
The chat box is empty.
The chat box is empty.
Okay, thank you, Semi. And okay, I'm gonna to talk about relative polio group, which is a generalization. The previous notion, namely, is a generalization of a polio group. This definition is a part of my work, my joint work with my PhD advisor, Dr. Rajai, which is independently defined by Chabert. So let's K over P be a finite extension of number fields. The relative polio group of K over P, which we denote by Po of K over P, is defined as a subgroup of the ideal class group of K, generated by the all generalized Ostrovsky ideals. They are defined to be the product of the all maximal ideals of K with the same relative norm of K over P, namely B equals to beta with power F. And in particular, note that the relative polio group of K over Q would be the ordinary polio group, which is defined by Xanthema, has been defined by Xanthema, and the relative polio group of K over K would be the whole ideal class group of K. And as a generalization of the Xanthema exact sequence in the previous section, we can find this generalization and gave an exact sequence as you see. And here the map epsilon denotes the transfer of ideal classes or ideal extension homomorphism from the ideal class group of P to the ideal class group of K. And again, as a corollary, as you see, if we assume that the class number of K and the relative extension degree of K over P are co-prime, then the relative polio group of P would be equal to image of the epsilon map of K over P. And you may consider this corollary and this exact sequence to the previous one, namely to the Xanthema exact sequence. And the relative case would be a generalization of Xanthema results. Okay. I will need this lemma for studying the pre-Pólya group of in even dihedral fields. So I want to talk about this lemma. This lemma relates the relative Pólya group for a tower of finite extension of number fields, and in particular, in part 2, if L over Q is the Galois extension, then the relative Pólya group of L over P would be a subset of the relative Pólya group of L over K. And you see that the sufficient condition is that L over Q is Galois. And there is no condition on the extensions K over P or L over P. No, I wanted to talk about Pólya odd prime dihedral extensions of Q, and as I said, by an odd prime dihedral extension, I mean a number field L, capital L, which is Galois over Q, and its Galois group is isomorphic to the index L, the dihedral group of order 2L for L and odd prime. And please Keep in mind these notations in this slide throughout this section, namely L is an odd parent dihedral extension of Q, E is the unique quadratic subfield of L, and K is a subfield of L such that L over K is a quadratic extension. We refer to such field K as a DL field. So by a DL field, we mean a number field with extension degree L such that the Galois closure of K over L has the Galois group isomorphic to DL. And I start this section with this fundamental lemma. This lemma describes the decomposition form of P in L, K, and E as well. And moreover, this lemma relates the principality of the Ostrowski ideals in L and in corresponding Ostrowski ideals in its subfield of L. Namely, for instance, whenever the ramification index of P in L for a ramified prime in L is 2, then the principality of pi index P of L is equivalent to principality of the corresponding Ostrowski ideal in E, and so on. It should be mentioned the proof for this lemma is accomplished by localization using ramification groups and considering the norm and epsilon maps for respective extension, for relative extensions. The main theorem in this section, a theorem which relates the Polio group of L to the Polio group of E and K. I recall that by K, I mean a DL field for L and odd prime. The capital L is the Galois closure of K over Q, and E is the unique quadratic subfield of L. Then we have an exact sequence, as you see. More precisely, the 2 torsion subgroup of POL is isomorphic to the Polio group of E, and the L torsion subgroup of POL would be embedded in the Polio group of K. And note that by Xanthema exact sequence, again, the Polio group of L should be a 2L torsion group, and so we can split this group to as the direct sum of 2 torsion subgroup and 2 L torsion subgroup as well. Okay, before I talk about an interesting consequence of this theorem, let me to give an example to be more clear at this subject. So let K be Q of theta, where theta is the root of the quintic and monic polynomial fx. As you see, then one can show that K is a D5 field. K has class number 4, and E equal to Q of square root of minus 3067 is the unique quadratic subfield of the Galois closure L of K. Now, since E is Polya by Hilbert's theorem, and the class number of K is not divisible by 5, then L is a Polya D5 extension of Q. And note that by the previous theorem, if the extension degree of K over Q, namely L, doesn't divide the class number of K, then the Polya group of L should be a 2 group and isomorphic to Polya group of E. And so we can talk about this corollary, which gives some sufficient conditions for that the Polya group of L and Polya group of E be isomorphous. And note that in the part 2, whenever L over E is unramified, by class field theory, the class number of E is divisible by L. And there is more generally, and conversely, if the class number of E is divisible by L, by class field theory, there is a cyclic unramified extension such M over E, with extension, but with relative extension degree L. In this subject, Tyra Hondra has proved that, I'm sorry, he gave the necessary and sufficient conditions for a quadratic field, so namely E, to have a class number divisible by 3. And as a generalization of Honda's result, we can found a sufficient condition for L over E to be unramified extension, and in particular, the Polio group of E and Polio group of L are isomorphic. Note that this corollary states in terms of a relation between coefficients of minimal polynomial of f(x), where L is the splitting field of the irreducible polynomial f(x). And I recall that again by capital L, I mean a DL extension of Q, and E is the uniquadratic subfield of L. Now I'm gonna to talk about maximum ramification in Polya dihedral extension of Q, and so I start with this upper bound due to Amandine-Lerish or Lerish maybe. This theorem says that for M over Q, a Polya-Galois extension of extension degree N, the number of ramified primes in M over Q is bounded by this number. And as you see, the Lerish upper bound is dependent on the extension of M over Q. And for example, in our case study, for whenever the degree of M over Q is 2L for L and odd prime, then by Lerish result, M will have at most L plus 4 ramified primes, which may be a very big number. On the other hand, we can find an improvement on these results, and we have found an upper bound independent of relative extension degree, and I should be mentioned that for here is an exception, namely for L equal to 3, and namely for non-Galois-cubic number field, and there's corresponding to S3 extensions of Q, K may be pure or non-pure, and I just state these results in 2 theorems. So let K be a non-Galois-cubic field and L be its Galois closure, i.e. L is a S3 extension of Q, and as usual denoted by E, the uniquadratic subfield of L. If we assume that L is Polya, then for L real, there are at most 5 ramification primes in L, and moreover, depending on solvability of equation norm, this upper bound can be made small to 3. And similarly, for whenever L is imaginary, for non-pure K and K pure, this upper bound can be made smaller to 2 and 3 respectively. And again, for the case that K is pure, depending on the solvability of equation norm, this upper bound can be made smaller to 2. And you can compare this upper bound with previous one, and we said that this improvement give a smaller upper bound, and moreover, the desired upper bound are short, as we will see. I start proof of this theorem by xanthoma exact sequence, and since we assume that L is a Polya, let me to back to xanthoma exact sequence. Since we assume that L is Polya, the order of H1 equals to the product of ramification indices, and where by G I mean the Galois group of L over Q. And now consider the cyclic subgroup of G, namely G2 and G3, corresponding to relative extensions L over K and L over E respectively. And using this fact that restriction map is injective on the 2 primary and 3 primary parts of cohomology group, we conclude that the order of H1 of G is would be a divisor of order of H1 of G2 times order of H1 of G3. So for finding an upper bound on the order of this term, we can find an upper bound on the order of the order of H1 of G2 and G3. On the other hand, since L over K and L over E are cyclic extensions and using Herbrand quotient, and since we know that the Herbrand quotient for the cyclic extensions of G2 and G3 can be computed, then it is sufficient to compute the order of H0 hat of G2 and G3, where by H0 hat I mean the zero-dimensional Tate cohomology group. Finally, you can use the image of norm map, and using the Dirichlet unit theorem on the rank of unit groups, we find that the product of ramification indices of P in L, which is equal to order of H1 of G and UL, is a divisor of these numbers. Namely, we can I separated them for 2 cases corresponding to L is real or imaginary. And finally, since L is Polya, by the main theorem of this section, namely this exact sequence, and we conclude that E is also Polya. On the other hand, as I said before, by Hilbert's theorem, and for a Polio quadratic field, there are at most 2 primes ramified. And finally, by the first lemma in this section, part 1 of lemma, we see that for each ramified prime P in E, the ramification index of P in L would be divisible by 2. Summing up this argument, we have the product of ramification indices would be a divisor of 2 with power 2 times 3 with power 2 whenever L is real, and similarly when L is imaginary, the product of ramification indices would be a divisor of 2 with power 1 times 3 with power 2 as well. And in my opinion, the proof can be complete here, because for counting the number of ramified prime is just sufficient to consider these powers. Namely, this term gives 4 and this term gives 3 as stated in theorem. Anyway, considering the solvability or non-solvability of equation norm for the cyclic extension L over E and L over K, the desired upper bound can be obtained. And before I continue my talk, it may be better if I stop and ask the Semi, are there any comments or questions, or should I continue?
At the moment,
dear Semi, do you hear?
Yes.
At the moment,
I don't have any questions, but if anyone does.
Okay. Okay, thanks, Semi. Thanks.
You're welcome.
I'm sorry about making you tired, but I will try to finish my talk as soon as possible.
There is no rush.
Just before giving, sorry, what?
Do we have a time? I mean, we have. I don't think we have a time limit. We can extend it beyond an hour. You don't have to go through it.
Many thanks. Many thanks. Yes, I will just try to finish my talk before 1 hour. Thank you, Sami.
You're welcome.
Okay, just before giving the generalization of the upper bound on the number of ramified primes in Polya dihedral extensions of Q, which is a generalization of the previous theorem, to show that the desired upper bound is sharp. Here you see some example to verify this. For example, this slide gives an example of a real Polya S3 extension of Q with 4 ramifications. Here is an imaginary, we find an imaginary Polya S3 extension with 3 ramifications, and L is a Galois closure of a pure cubic field. And finally, this slide gives an example of an imaginary Polya S3 extension with 2 ramifications, and L is the Galois closure of a non-pure cubic field, as desired in the previous theorem. And more generally, for a dihedral extension, a DL extension, or for an odd prime dihedral extension L of Q, for the extension degree of L over Q is 2 times an odd prime, we can find a similar upper bound to the previous one, as you see, but I omitted the proof because the proof was very similar to the previous one. Instead of, please note that here is an exception. In this case, namely for whenever L is greater than 3, whenever L is imaginary, then one can show that the relative norm of L over K is surjective, and the upper bound for the part 2, namely for L is imaginary, should be 2. And however, we will not, we cannot prove the sharpness for general case. The sharpness of these upper bounds for general case have not yet been proved by now. And the final subsection, the last subsection of this part is about a result due to Ishida, where he has proved for K over Q a non-pure extension of degree N, if the number of totally ramified primes in K is greater than Dirichlet unit rank of OK, then the class number of K would be divisible by extension degree of K over Q. And as you see again, the Ishida's upper bound also depended on the extension degree of K over Q. And for instance, in our case study, namely for DL field K, for L and odd prime, and using the signature of K, namely considering the real embedding and complex embedding of K, for the discriminant of K is positive or negative, and by Ishida results, if at least L or respectively L plus 1 over 2 primes ramified totally in K, then the class number of K would be divisible by L. And you see again here the Ishida's upper bound is dependent on the degree extension. As a corollary of the previous theorem and previous proof, we can use again Herbrand quotient, computing cohomology group, and so on to find an upper bound on the number of ramified totally primes in K for a DL field K to make the class number of K divisible by L. And as you see this corollary, for instance, for case 2.1 in part 2, if L is greater than 3, and whenever K has positive discriminant, and if there are at least 3 totally ramified primes in K, then the class number of K is divisible by L. And these upper bounds these upper bounds don't depend on the L. On the L, by L, I mean the extension degree of K over Q. For instance, I give a short proof for case 3, namely for the case K is a DL field for L is greater than prime, and K has positive discriminant. If we assume that there are 3 distinct prime totally ramifying K, then L with power 3 should be a divisor of product of ramification indices in L. And this relation is obtained by the first lemma in this section, and by Xanthema exact sequence, this term would be equal to order of H1 of the Galois group of L over Q times the order of the Polio group. On the other hand, the order of the H1 of Galois group of L over Q would be a divisor of a power of 2 times L with power 2, which implies that the Polio group of L is the order of the Polio group of L is a divisor of, it is divisible by L. And the main theorem of this section, namely this exact sequence, and we have seen that the L torsion subgroup of L would be embedded in Polio group of K, completes the proof. It should be mentioned also, recently Schabert and Halberstadt have proved that in the DL fields K, whenever L is an odd prime, then the Polio group of K would be equal to the whole ideal class group of K. And the last section of my talk, I'm gonna to talk about non-Galois extension, as I stated before, investigating on Polio group and Polio fields are more difficult than the Galois ones because, as we saw before in this slide by Ostrovsky remark, for Galois extension, the Polio group of K is would be generated by Ostrovsky ideals for ramified primes. Besides, for non-Galois ones, we have to consider all primes, ramified or non-ramified primes. Based on these remarks, recently Schabert and Halberstadt, and as a generalization of Polyon's condition due to Xanthema, Schabert and Halberstadt defined the notion of pre-Pólya group or non-ramified Polio group of K, which is a subgroup of Polio group of K, and is defined to be a subgroup of PoK generated by all classes of Ostrovsky ideals corresponding to all non-ramified prime in K. And as you see, for a Galois extension K over Q, pre-Pólya group of K would be automatically trivial. There is also another notion, namely Po of K with index NR1. It should mention, I don't know what name is appropriate for this subgroup, and I just refer to this group as Po of K index NR1. Po of K index NR1 is defined to be, is generated by all classes pi index P1 of K, where P is a non-ramified prime in K, and for this group we will consider all Ostrovsky ideals corresponding to residue class degree 1. Based on this definition, recently the same authors, namely Schabert and Halberstadt, proved that for a Dn field K, when n is an odd integer, not necessarily prime, for an odd integer, we have these equalities. And it should be mentioned that Dn field K is an example of a Frobenius extension, and by Zanzema sequence and by Schabert sequence, there are more general results that says for all Frobenius extensions, these equalities hold. But this theorem motivates us to take K be a Dn field for an even integer to complete this classification. So I'm gonna to talk about my new results about pre-Pólya group of even dihedral extension, which is the last section of my talk. Okay, I start with this fundamental lemma due again to Zanzema. Actually, this lemma is proved by Zanzema results, which says that whenever K is a Dn field for an even integer and denotes by a unique subfield of degree n over 2 over Q by F, then the relative norm map of the ideal class group of K to the ideal class group of L is surjective. And in particular, the class number of F will be a divisor of the class number of K. Proof is simple because of Zanzema has proved that there is always a prime of F which is ramified in K, and by well-known results in class field theory, we know that for a general extension, not necessarily quadratic, if there is a prime of P which ramified totally in K, then the relative norm map is surjective, which implies that the class number of F will be a divisor of the class number of K. We will use this lemma to for proof an interesting corollary of the main theorem. This is the main theorem of this section, and which completes should be complete the results about Polio and pre-Pólya group of dihedral number fields, and that says that for a Dn field K for an even integer and the unique subfield of K of degree n over 2 by F, then these equalities hold in particular the pre-Pólya group of K, and the image of the epsilon map of K over F would be equal. For proof, we need some technical, group theoretical techniques, and using some facts in class field theory. And I will try to give a short proof and pass this proof. So let's H of K be the Hilbert class field of K, namely maximal abelian unramified extension of K, and n index H be the Galois closure of H of K over Q. And you are using Galois theory denoting these groups, and note that by class field theory, the quotient group of H over H1 would be isomorphism to the ideal class group of K, and similarly, the quotient group of J over J1 would be isomorphous to the ideal class group of F. Now, considering the set of all right coset of H in G, and considering the action of G on omega, by omega I mean the set of all right coset of H in G, and these corresponding we can find for each I a right coset HSI belong to the orbit of Pi, where P1 to Pt would be corresponding to G for an arbitrary elements of Galois group, and Pi are disjoint cycles of order Fi. By cycle, I mean a permutation on the symmetric group on symbols denoted by S index n. Note that all this computation can work for an arbitrary number field, but here there is an exception for even dihedral number field, as we will see. So let P be a non-ramified prime in K, and beta be a prime of n index H above P, and let G be the Frobenius element of P in the extension n index H over Q. And one can show that this result actually is due to Zantema again, which is reformulated recently by Chabert. We have this equality where this notation, namely pi index P with power F of K over HK over K, denotes the Artin symbol of the Ostrowski ideals, pi index P with power F of K. And so using Artin reciprocity, we can find this one-to-one corresponding, and more generally, we have found this corresponding. And this is the same exception that I said because of in the case that K is an even dihedral number field for each non-ramified prime P, if P has a various residue class degree, then the decomposition form of P in K should be on this form. And using this equality, one can see that pi index P with power P with power of 1 of K is principal if and only if the Ostrowski ideal with residue class degree 2 is principal. This proved the first equality, namely by this relation we see that the pre-Polya group of K would be equal to pi of K with index nr1. And for proving the second equality by Galois theory, since the index of H in J is 2, and taking S1 be the identity elements of the Galois group, and S2 belongs to J minus H, we can see this corresponding, and considering these elements, namely GS inverse modulo H1, we can prove that the pre-Polya group of K would be isomorphic to image of a map, which is compositium, the transfer map, and a map, namely I, induced by the inclusion map. Now, by the first lemma in this section, we know that this norm map is surjective, which implies that so is I. And considering the following commutative diagram of abelian groups, the proof is complete and the desired equality can be obtained. Note that the vertical arrows in this commutative diagram are induced by the Artin map. Okay, I'm gonna to talk about a number of an upper bound on the maximum ramification in Polya D4 fields. And just before that, let me to talk about an interesting corollary of the previous theorem, which says that with the same notations, namely K be a Dn field for an uneven integer, and the unique subfield of K of degree n over 2 over Q by F, if we assume that K has odd class number, then these equalities hold more, and in particular, the pre-Polya group of K would be equal to Polya group of K, would be equal to the relative Polya group of K over F, and would be isomorphic to the ideal class group of K. And the proof is obtained by using some previous results. And just note that since by the first lemma in this section, h of k is a divisor of is divisible by the class number of f. So we can conclude that the corresponding epsilon map of the ideal class group of f to ideal class group of k is injective. Okay, and it may be good if we have an example of this corollary, and we can use Charles Parry criterion, where he has found the necessary and sufficient conditions for pure quartic fields to have odd class numbers, to have odd and even class numbers. And in particular, he has proved that for a prime p congruent to 3 modulo 8, these families of pure quartic fields have odd class number. And using these Parry results, we can see this equality hold. For instance, we can see that Q of fourth root of 2 times 59 with power 2 is a Polio field with class number 5. And the last section and the last part of my talk, as I said, is about maximum ramification in Polio D4 fields. Again, I have found an improvement on Xanthema's results, where he has proved for a Polio D4 field, there are at most 5 ramified primes. Whereas in his paper, he asked, he know whether this upper bound is sharp or not. And recently, Schabert and Halberstadt gave an example to show that the upper bound 5 is sharp, actually is sharp. And yet we can find an improvement these results, as we will see. For giving an improvement, I need 2 lemmas. The first lemma is about an upper bound on the rank of relative Polio group of K over F, where K is a Polio D4 field and Fe denotes the unique quadratic subfield of K, and proof is easy. And the second lemma is about the counting reasoning about the number of ramified parameter K over Q dependent on which is dependent on number of the ramified parameter of F in Q and the rank of relative Polio group of K over F. And now we can talk about the upper bound on the maximum ramified primes in Polio D4 fields, D4 fields. I'm sorry, D4 fields. Please just note that we cannot generalize this theorem to arbitrary Dn fields because of the only case that F over Q is Galois is the case that's in B4. And this theorem works here only for case D4 fields. And as you see, the only case the upper bound 5 can occur is the case that F is real, F has no units of negative norm, and there are no ramified infinite place of F in K. And proof is obtained by using main theorem of generalized Xanthema exact sequence. We can find the order of relative Polio group. Then we can use the upper bound, the desired upper bound on the rank of the relative Polio group. And finally, using the Herbrand quotient for the cyclic extension of L over K, the desired upper bound can be obtained. However, we write here only the case that F is imaginary. But the similar proof can be obtained for the case F is real. So I finished my talk, and I'm so sorry for making you tired, and I'm so grateful for FGC and IPM mass organization to permit me to have a talk in this seminar. Thanks of all. Okay. You're welcome. Thanks, Professor Ilham. Any comments or questions? I'm so sorry making you tired, and so grateful for your coming in this seminar, and I hope to have see you again in the next seminars.
Thanks for the talk,
Okay.
Abbas.
Thanks for the talk.
Thanks, Samir, for your many works.
I have one question.
I have one question.
Can you sort of
yes.
summarize what makes dihedral group special in the arguments and the techniques, and what the reason for choosing to study dihedral extensions, and if there is a way of extending the result for other extensions from Xanthemel's sequence.
Yes, of course. From Xanthemel's. Many thanks for your questions. I should be mentioned before. I'm sorry, I forgot it. Let me share a screen again and talk on slides. Okay. I'm sorry, just a moment. Investigating on Polio fields and Polio groups have many results, and as I said, this Xanthema exact sequence is a main tool for investigating on Polio group and Polyaness of number fields K. The first motivation for us to investigate on dihedral fields dates back to results due to Lerish, where she has found results about Polyaness of Galois closure of pure cubic fields, and I didn't talk about some Lerish results. However, there are two separated sections, namely Galois and non-Galois bonds, and in the Galois section, the first case, the non-abelian Galois group occur is for S3 extensions. Yes? So, at the first, I will generalize Lerish results on Polyaness of pure cubic fields. I'm so sorry, my connection is right. Do you hear me, or my connection is broken?
We can hear you, it's just that the screen
Sorry, I'm so sorry. I'm so sorry. I'm sorry. So, as I said, at the first, I generalized the Lerish results on Polyaness of pure cubic fields to general S3 extensions of Q. Yes, and more generally, we have seen that we can generalize our results to general odd prime dihedral number fields. On the other hand, odd prime dihedral fields has a nice structure group because of, as you saw in my slides, we can use Herbrand quotient for the cyclic extensions L over E and L over K, and their relative extension degrees are co-prime. Can you hear me?
Yes, it's just your voice just got cut off for a second.
Your voice just got cut
we
off.
can.
I'm so sorry.
I can hear you.
Okay. So I should again my answer. And as I said, at the first, we generalized the Lerish results on polyaness of pure cubic fields to general stereo extensions, and then we can generalize our results to odd dihedral number fields. On the other hand, the odd prime dihedral number fields have a nice group structure because of, as you saw in my slide, we can use Herbrand quotient for the corresponding cyclic extensions which have co-prime relative degree extensions, namely 2 and L. And by the assumption, L is an odd prime. And we can use the Herbrand quotient, and we can use injectiveness of restriction map to find an upper bound on the order of the first cohomology group of Galois group of L. But for n, whenever n is even, n is an even, we have used a different method to find result. More generally, we can yet generalize these results to Frobenius extensions. As I said before, Schabert and Halberstadt gave a new results in this area. I don't know my answer was exactly to your question, and so please let me know if I should explain more.
I think that's enough. Thank you.
I think that's enough. Thank you.
Thank you for your coordinating and for your work. I know I have made you tired for organizing these seminars, and I'm so sorry about that. And it's my pleasure to you have a talk in these seminars as you want.
Thanks for sharing your
I have talked to my advisor, Dr. Hedayat, and he permit me to fix a date for your talk in the next future and in the next weeks.
Okay.
Okay.
Please let me know if whenever you have fixed your date of your talk and
yes,
other speakers. And Semia, just to be sure, the next speakers, our speakers would be Oliver or
Gülçel.
Oliver Gülçel.
Okay. And we will inform the invited guests to for exact date and time of the next talk in these seminars. Yeah. I think my connection is broken or okay. Oh yeah, 2 weeks from now. Yes, many thanks of Professor Ilhan. Yes, 2 weeks from now. And the next speaker would be Dr. Olivier Buelchel. Am I right? And will inform you with FGP IPM email. Many thanks, and I'm so grateful to have a talk in these great seminars. And I'm so again apologize for making you tired. Okay. Thank you, Professor Ilhan, and anyone else. Nice to meet you and see you again in 2 weeks from now. And so I want to finish this meeting if there are no questions or comments.
Sorry, I have questions and I raised my hand.
Yes, yes.
In fact, if you
I'm so
share
sorry.
a slide, no problem.
Of course.
Yeah.
No. I share now.
In slide 18, please.
In slide 18.
Yes.
The exact sequence is
this
very, yeah.
The exact sequence is very, yeah.
This exact sequence is very look like to inflation restriction sequence of cohomology.
Inflation restriction sequence of cohomology.
So
yes, of course. Yes, of course.
Is the proof of this theorem related to this exact sequence of cohomology, or
this exact sequence of cohomology, or
this relationship is only
not
accendic?
Exactly.
This relationship is only accendic.
Not exactly, dear Ehsan. Actually, for proof, I will use some computation tools, such as like as the proof for the first lemma in this section. Indeed, for proof, we use injectiveness. We prove the injectiveness of this map. Compositium of the relative norm map of L over K, and the pi index L means that multiplication by 2 or projection on L components of the group. Okay, and on the other hand, we strictly proved this epsilon map is injective. And we didn't use a restriction or inflation map for proof exactness of this sequence as well.
Oh, so this shape is
but
only
your comments your comment was interesting. There is a similarity for this exact sequence and restriction inflation map. Yes.
Thank you.
Yes.
And another question is about
I don't know. My answer was exact. No.
Yeah, exactly.
Yeah,
exactly.
The slide 42.
The slide
please.
42. Please.
Yes, I'm so sorry. 42.
Yeah.
Yeah.
Okay, slide 42. Yes.
Yes, yeah. In the corollary, you write this equality that is very interesting. And my question is about a thing that until now not appear in the literature, but you know it. What happens for the Ostrovsky group of K over F? I mean the quotient of relative Pólya by the co-kernel that appeared in the main exact sequence.
Relative Pólya by
the co-kernel of the epsilon
relative
map.
Pólya by
the co-kernel of the epsilon map.
Yes.
That exactly appeared in the exact sequence of relative Pólya.
Exact sequence of relative Pólya.
This exact sequence, yes.
Yeah, exactly. You consider the quotient at the right together and call it the Ostrovsky group of K over
the right term. You mean the right term.
Yeah. Because the relative Pólya group does not controlled by ramification, but Ostrovsky group controlled by ramification.
Yes. If I understand correctly, your question is that what is the general structure of this quotient group?
Yeah.
I have not studied more on this quotient group because we were interested just for the order of the relative Pólya group, and using this exact sequence we can found we have found this equality, right? But for studying the structure of the relative polio group, it may be a good subject for study because of unlike the classical type, namely for the case when we consider K over Q, for the relative case, at the best of my knowledge, there is no results about the structure of Ostrovsky or Polio-Ostrovsky group and its relation between the image of the map epsilon for the general case.
Yeah.
And again, I don't know. I gave a right answer, and I understand your question.
Sure.
But, so please let me know if I should explain more.
No, very good. Very good. Thank you very much.
No, very good.
Thank you, Hassan. Yeah, your questions were interesting.
Thanks a lot. And thank you for very interesting talk.
We'll think about them.
Thank you for very interesting talk.
You're welcome. Thank you for your coming, and thank you all again for your attention and your time. Many thanks. Are there any questions? Okay, so let me stop the record.